This section is about binaries, encoding and decoding, ASCII, and Unicode. We want to learn about encoding and decoding. We already know that computers can only understand binaries, zeros or ones. The hardware and software running on your computer must translate everything into a finite binary sequence. Translating from one set of symbols to another set of symbols is called encoding. For example, ASCII to binary or integer to binary. When we put files, they are encoding to binaries. Decoding is the opposite, translating from the encoded symbol set back to the original symbol set. For example, binary to ASCII, binary to integer, like when we hear music or when computer shows something on a screen, it decodes that information for us.
Modern-day computers use electricity to work, and inside of a microchip, electricity is turned either on or off, which is represented by the symbols 1 and 0. This is called binary. You've probably heard of binary already, and that's how computers work. But do you know how binary works? Well, you're about to find out. But first, we need to understand exactly how our numerical-based system, known as decimal or base 10, works the way it does. So, there are 10, count them, 10 symbols that we use for all of our numbers. Starting from 0, we can count all the way up to 9 before we run out of symbols to use. Now, we could just keep adding symbols at this point, but that would get out of hand very quickly. I mean, can you imagine having to memorize a specific symbol for every single number? That's ridiculous. And that's why we reuse the same symbols over and over again in a very clever system called positional notation. So, in the base 10 system, as soon as we get to 10, or an exponent of 10, we need to add another digit to the left of our current digit. Because there are 10 symbols, each new digit has to have a value 10 times greater than the digit to its right. So that's using 10 symbols. But what if you had only 2 symbols to work with? Well then, everything that I said still applies. With just 2 symbols, each new digit needs to have a value 2 times greater than the digit to its right. So a sequence like this would equal 1 times 128, plus 1 times 16, plus 1 times 8, plus 1 times 2, plus 1, which is 155. And that's how you count in binary. It's actually really simple. It's just multiplication and addition. Now, it gets a lot more complicated from here, with bits and bytes and Boolean logic and ASCII, and the list just goes on and on. So let's return to base systems. There are a lot of ways to write numbers other than decimal and binary. You've got base 2, base 3, base 4, base 5, I could go on. They all work with the same principles of positional notation. So you might be wondering, with all these numbering systems to choose from, why do we use base 10? That's a good question. This goes all the way back to Roman numerals and Egyptian hieroglyphs. It's likely that we use base 10 simply because we have 10 fingers, also known as digits. Other base systems like base 8 and base 12 are actually superior for simple everyday math, since 8 and 12 are much more easily divisible than 10. But it's definitely too late to change our minds about using base 10. We'll probably be stuck with it forever. Switching away from it now would be even harder than trying to convince America to drop the imperial system and finally switch to metric. You know, like the rest of the civilized world. Like, yeah, the metric system is superior, but who's gonna tell America what to do? Now, if you're going to be using base 12 or any other base system with more than 10 digits, it's standard to use letters to represent numerals higher than 9. So 10 is A, 11 is B, 12 is C, and so on. This is called alphanumeric. You know those URL shorteners that you see on Twitter and elsewhere? Have you ever wondered how they work? All those jumbled characters really just represent a very large number. By using numerals and every letter of the alphabet, you can get all the way up to base 36. Using lowercase and uppercase letters gives you base 62. And with that, you can get all the way up to 14 million with only 4 digits. With just 10 digits, you can get up to 839 quadrillion possible values. That's a lot of shortened URLs. So, you just learned about positional notation, binary numbers, numeral-based systems, alphanumeric characters, and URL shorteners.
Computers only work with 0 and 1, that is off and on. And if I have 1 bit of memory, in that 1 bit, I could only put 0 or 1. So the numerical system that I'm using is 2. And how many places I had? I only had 1 bit. So 2 to the power of 1 equals 2. This 2 means this states I had only 0 and 1. Let's say if I had 2 bits. If I had 2 bits of data, I can put it 0 and 0, 0 and 1, 1 and 0, 1 and 1. So if I have the binary system with 2 places, I can have 4 states. I can have 4 codes actually. 0, 0, 0, 1, 1, 0, 1, 1. It's like locking a door that could have some codes. We can use these codes. Or for example, if you have 3 bits here, what can we do? What can we put here? I can put all of them 0 or 0, 0, 1, 0, 1, 0, and then 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. What else? 1, 1, 1. Okay, as you saw, 2 to the power of 3 bits. 2 is the binary system because we have 2 digits. And then here I can have 8 states. I can have 8 codes. Okay, you got my point. In binary system, if I had 4 bits, how many states, how many codes I can have? Right, 16. If I had binary system with 5 bits, I can have 32. If I have binary system with 6 bits, I can have 64. If I had 8 bits, I can have 128 codes. If I have 8 places, 256. Yes, as you see, every time it gets double. 2, 4, 8, 16, 32, 64, 128, 256. Okay, let's clear the screen. Okay, in the video we've already talked about how many codes we can have if we had 1 bit, 2, 3, or 4 bits of memory. I want to tell you how we can convert decimal to binary. That would be encoding, and also vice versa. A binary to the decimal, that would be decoding. So encoding is what? Decimal to binary. Let's learn this one. If I have, for example, what? Number 21 in decimal. I want to change it in binary system. What it would be? By division, I should just divide 21 to 2. That would be 10. The remainder would be 1. Then again, 10 divided by 2 would be 5, and that would be 0, the remainder. And then I can divide the quotient 5 to 2. That would be 2. It would be here 4, and the remainder would be 1. And then here 2 divided by 2 would be 1, and I can have 2 and the remainder would be 1. I don't continue dividing because this quotient is less than the divider, okay, the denominator. And then so because it's less than this, it's smaller than this, so here it's enough. I stop here. What I do is let me change the color, and I'm gonna tell you here. Okay, what I do, I write these ones and zeros from right to left. So this is 1, I put this 1 here, 1, then 0, then 1, 0, 1. So that would be the answer for converting 21 to the binary. Okay, this is a little bit hard and time consuming. I'm going to tell you an easy way. So for converting 21 to binary to the base 2, I can just have a table here. Let me change my color. Okay, I can have, give it back. I can have a table, and then here I can have 1. I would double it 2. I would double it 4. I would double it 8. I would double it to 16, and I can continue. That depends on the number. And then I have 21. I want to convert to 21. So 21, let's continue this once more. 32. Okay, I have 21. So 21 doesn't contain 32. It's less than 32, but it can contain 16. So I put 1 here. And then I deduct 16 from this, so I can have 5. 5 is less than 8, so I don't have any 8 in that. But 5 is bigger than 4, so I can have 1 4 in this. Then I deduct 4, I can have 1. 2 is bigger than 1, so I don't have any 2 in this. And then I have 1. Okay, let's see if they are equal. 1 0 1 0 1. This is exactly the same as this one, so it means we did it correctly. Let me give you another example. Okay, here, let's say I want to change 94 to binary. I'm going to change the color. Okay, again I draw the placement table, and let's see, I have 1, 2 double it, 4 double, 8 double, 16 double, 32 double, 64 double, 128. Okay, so now what? I compare 94 is less than 128, so I don't have 128. But I can have 164 in 94, so I put 1. Okay, let's see What's the remainder? 94. I would just do it here. 64. I can have 30. Okay, 32. No, I don't have 32. I can have 16. So if I just deduct 16, that would be 14. Okay, I can have 8. If I deduct 8, I can have 6. I can have 4. If I deduct 4, I can have 2. I can have 2, and I don't need this one. So this is the number for the binary. So that would equals 1, 0, 1, 1, 1, 1, 0. That's the binary number I can have. So that's the digits that the computer stores. Instead of 94, it stores this number. So what if I want to do decoding? So that was encoding. This is another example to convert this binary to a decimal. Let's do decoding. What's going to happen? I have 1, 0, 0, 0. This is in binary. What would be in decimal? Again, I draw that table. That would be easier. So 1, 2, double, 4, double, 8, double would be 16, 20, whatever. Okay. And I put these numbers, the numbers that I have, 0, 0, 0, 1. Now, what do you think? Yeah, that would be 8. That's it. So this code is equivalent to 8 in decimal system. Let's have another example, okay? For decoding, I have 1, 1, 0, 1, 1. Okay, what's the equivalent of this? I can just have it here. I draw the table. Okay, now here 1, 2, 4, 8, 16. That's enough. Okay, 116 equals 16. I have 1, 8. I have 1, 2. I have 1, 1. So that would be what? 24, 26, 27. So this number is equivalent to 27. We decode it. So that's how computer systems work. I hope that was helpful for you and you learned from this. Okay, let's see how many bits we need if we want to have n different symbols. For doing this, we have a formula for this, that we get the ceiling of logarithm of that n, the number base 2, because we are working with binaries. That's so obvious. So here, if we want to explain it in a plain English, just imagine I need to encode to assign 30 different codes to 30 different things. For doing this, I just convert 30 to the binary. So after conversion, I have 11110. That means I need 5 bits. So this is one way just to figure that out. Another way is just to use this formula and to get log of 30 that we can obtain 5. So I need 5 bits to assign 30 different codes. Non-negative integers are integers greater than or equal to 0. The numbers we already converted on previous slides are unsigned numbers. They're actually positive. So we already worked with unsigned numbers. However, Java uses signed integers with a fixed number of bits. If we want to work with signed bits, we need some padding. So here in this example, let's see x to the index of b denotes the integer greater than or equal to 0 in base 2. So for this example, 5 equals to 101 as we already learned, but we put some zeros because we want to assign 1 bit. So the back bits would be 0. That doesn't change the value of 5. With signed numbers of fixed length in binary, typically the leftmost bit will be a negative power of 2, and if the leftmost bit is 0, then the number is positive. If the leftmost bit is 1, then the number is negative. Let's explain unsigned and signed numbers here in this chart. If you remember this chart from previous lectures, we had some data types in Java that assigns some memory, some bytes to this one. For example, for the first one, that the data type that is byte, Java assigns 1 byte of memory, but the range is from negative 128 to 127. Actually, 2 to the power of 8 bits, that equals 1 byte, would be 256, but as you see, it would be divided by 2, so that would be from 128 to 127. That equals this range of codes. If you look at short, that is integer, and it assigns 2 bytes. 2 bytes equals 2 to the power of 16. That would be 65,535. That if you divide it by 2, so the range, because we want to have negative numbers, so the range would be from minus 32,768 to 32,767. So this is the same for int, long, floats, and the rest. But if you look at char, you see that although it assigns 2 bytes or 16 bits, but because we don't use any negative or signed numbers in there, so we can assign all the 65,535 different codes to characters. Alright, why all these mathematics are important in computer science? Let's take a look at the tweepocalypse that happened in June 12, 2009 when Twitter crashed. The reason was that the unique numerical identifier associated with each tweet exceeded the limit of 32-bit signed integers. So now, as a computer scientist, what solution do you recommend? Let's talk about ASCII text encoding. ASCII stands for American Standard Code for Information Interchange. 7-bit and 8-bit ASCII is one of the most widely used text encoding schemes. The ASCII chart contains all of the symbols that you can see in English keyboard, like all the letters, numbers, and symbols. It was developed in the US to encode symbols in English language, which is easily encoded with 128 symbols. Alright, let's look at the ASCII character chart. What we can understand from this. These are the integer representations of all the characters that you have on your keyboard. But in this part, codes 0 through 31 are called control characters that are performing in the background. But here, the first code, 0, represents null. And just be careful about space, that the integer representation of this is 32, so they are different. So when you assign these as strings or as characters, just notice that they are completely different characters. And here we can see that numbers 0 through 9 are sequentially here, and they are assigned 48 through 57 integers. And after numbers, we can see capital letters that begins from 65, A with capital A, and then it follows, and lowercase letters start from 97. One thing to note is here that the distance between capital A and lowercase a is about, if we deduct 97 and 65 from 97, you can see that that is 32, and this is equal for all the other letters like capital B and B, capital C and C, capital D and D. All the difference, the distances are 32. So that is how Java switches between lowercase and uppercase letters. If you find out the Bender's apartment code in decimal, you should get 36, and 36 in the ASCII chart is equal to $sign that represents the Bender's character in the movie. What is Unicode? The ASCII character set is too small to encode text found in different spoken languages throughout the world. So 16-bit Unicode can encode 2 to the power of 16, that is 65,536 symbols. And Java uses this 16-bit Unicode for characters. And also we have 32-bit Unicode that encodes 2 to the power of 32. The first 256 characters of Unicode are the same as ASCII character set. Thus, the ASCII character set is a subset of the Unicode character set. Okay, congratulations! You've learned a lot of things so far. In this chapter, you've learned about Java primitive types, assignment statements, operators, and expressions. Also, you learned how to input a value from the keyboard by the user and how to display them. We also learned about strings and all their methods and how to put some comments in the code. If you need, please go back and watch the videos, and wherever there is an activity, pause the video and try to give a response to them. Besides, if you can, practice the book examples to learn more. Thank you.